Here's a postulate, and you probably remember that a postulate is a statement assumed to be true without proof. This is called the segment addition postulate. If 3 points A, B, and C are collinear, and point B is between points A and C, then segment AB plus segment BC is equal to segment AC. And here's a picture of those 3 collinear points. B is in between the other 2. There's segment AB. We add on segment BC, and I hope you'll agree that the result is segment AC. And here is a related postulate known as the angle addition postulate. Let's go right to the picture. We have 3 rays with ray AC between the other 2. And this postulate states that the top angle, shown in blue, angle BAC, plus the bottom angle, the adjacent angle, shown in orange, angle CAD, when you put those 2 together, you get angle BAD. And here's theorem 8. If a segment is added to 2 congruent segments, the sums are congruent. This is also part of a series of theorems that are related to something called the addition property. In order to add the same segment to 2 congruent segments, they must be arranged something like this. Our congruent segments are given as AB and CD, now shown in blue. The segment we're adding to each one, of course, is segment BC, shown in orange. And what this theorem is going to prove is that the distance from A to C is the same as the distance from B to D. We're given then that segment AB is congruent to segment CD, and we're going to prove that segment AC is congruent to segment BD. And all of the theorems in this lesson are related, so their proofs are also very similar. I'm going to show the proof for just the first of the several theorems in this lesson. And for this proof, we're going to use the paragraph proof method. Well, we've stated the given that AB is congruent to CD, and we've stated what we're trying to prove, that AC is congruent to BD. So in our paragraph proof, we state that if the 2 segments are congruent, their measures are equal. And then we use the segment addition postulate to show that AB plus BC is AC, and BC plus CD is BD. And we write that down in line 2. And then, if the sum of 2 segments is equal to a third segment, in line 3 we point out that the sum of the measures of those 2 segments must equal the measure of the third segment. And now we use the substitution principle. In line 1 we noted that AB is equal to CD, so we're going to substitute AB in for CD in line 3 and then rewrite it with the substitution in line 4. So now in line 4 we have BC plus AB is equal to BD. And then we notice that in line 3 we have an AB plus BC, and in line 4 we have a BC plus AB. And our old friend, the commutative property, comes into play. AB plus BC, of course, is the same as BC plus AB. And since one of those expressions is equal to AC and the other is equal to BD, then AC must equal BD, and that's what we've written in line 5. And then if the length of AC is equal to the length of BD, we know that AC is congruent to BD, and we've now proved theorem 8. Here's theorem 9. Very similar to theorem 8, only it has to do with angles. Theorem 9 states that if we're given angles in this arrangement shown here, and we're given that 1 and 3, the blue ones, are congruent, then if we add angle 2, the one in between, to each one of those, the resulting angles, angle AFC and angle BFD, are congruent, and they're the ones shown in orange. And here's theorem 10. If congruent segments are added to congruent segments, the sums are congruent. So we'll start with a pair of congruent segments. Those are orange. We'll add 2 congruent blue segments to each one. So that means we're given that AB is congruent to XY and BC is congruent to YZ. This theorem proves then that the entire segments, in this case AC, is congruent to XZ. Theorem 11 is related to theorem 10 only with angles. We're given 2 congruent angles marked with blue arcs. And then we add 2 more congruent angles, 1 to each one, the orange arced angles, 2 and 4. That means we're given that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4. And then this theorem proves that the sum, angle 1 plus angle 2, is equal to the sum of angle 3 plus angle 4, or the way we've labeled it, angle ABC is congruent to angle XYZ. And in Theorem 12, if a segment or angle is subtracted from congruent segments or angles, the differences are congruent. Theorem 12 could really be split into two theorems, one theorem for segments and a second theorem for angles. But to save a little space, we combined them. Both parts of this theorem are related to a broader category called the subtraction property. We'll start with segments. And we're given that AC is congruent to BD, which are both marked with green segments. And we're going to subtract out the middle part, the BC, and what we're left with is that AB is congruent to CD. For angles, we're given three adjacent angles that look like this. Angle AFC is given as congruent to angle BFD. We're going to subtract out their overlap, which is angle 2, and that's going to leave us with angle 1 congruent to angle 3 shown with blue arcs. And now one more theorem that could also be divided into two parts. If congruent segments or angles are subtracted from congruent segments or angles, the differences are congruent. Once again, we'll start with segments. Here's our congruent segments. And then we're going to subtract the blue ones, which are given as congruent. And what's left, the two black ones, BC and YZ, are congruent, now marked in orange. So we're given that the entire segments were congruent, AC and XZ. We were also given that the blue segments, AB and XY, were congruent. And when we removed the blue segments, we were left with the congruent orange segments, BC congruent to YZ. And this related theorem with angles, we're given this. The entire angle ABC is equal to the entire angle XYZ. We're also given that angle 1 is congruent to angle 3. So when we remove angle 1 from the top and angle 3 from the bottom, we're left with angles 2 and 4. So angle 2 must be congruent to angle 4. Well, let's just review what these statements have told us. If we're given that those two red segments are congruent, AB and CD, then if we add the part in between, the BC, that should give us that AC is congruent to BD. And in the related theorem that involves subtraction, it's actually the converse. If we're given that AC is congruent to BD, we subtract the overlap, the BC, and we're left with AB congruent to CD, the subtraction theorem. And now let's work a problem that involves segments. We're given AD is equal to 16, that's the entire segment, and then from the diagram, we're also given that AB is 6 and CD is 6, which means that AB and CD are congruent. We can make several conclusions. One conclusion, of course, is that AC is congruent to BD by applying our addition theorem. And another is that the part in the middle is 4 units long, and we get that by doing 16, take away 6, take away another 6, and we get 4. Then, of course, we can add 6 plus 4 to get that both AC and BD are 10 units long. Here's another problem. This time we're given that the middle segment, the BC, is 9 units, and the whole thing is 33 units. We're also given that AC is congruent to BD. We can conclude several things. First, that AB is congruent to CD. Then, that AB and CD are both 12 because we do 33 take away 9 to get 24. But since the 24 consists of both AB and CD combined and they're congruent, we do 24 divided by 2 to get 12. And one more conclusion we can make is we add the 12 plus the 9 to get that both AC and BD equal 21. And for angles, we know that if we're given that angle 1 is congruent to angle 3, we can add angle 2 to both of those angles and get that angle AFC is congruent to angle BFD. And the converse of that is true. If we're given that angle AFC is congruent to angle BFD as shown, then we can subtract angle 2 from both of those angles, shown with the blue arcs, to get that angle 1 is congruent to angle 3. And here's a problem that involves angles. We're given that angle 1 is congruent to angle 3. Angle 1 is 40 and angle 2 is 20, so we write the 40 and the 20 up. And then we can note that angle 3 is also 40 because 1 and 3 are the same. And we can make a few other conclusions. one of them being that angle AFC is congruent to angle BFD. We can also conclude that both of those angles are 60 because 40 plus 20 is 60. And finally, the entire angle is 100 because 40 plus 20 plus 40 is equal to 100 degrees. Here's one more problem that deals with the angles. We're given that ray SL is perpendicular to ray SC, angle LSB is congruent to angle ASC, and the measure of angle LSB is 70 degrees. So we can conclude that the measure of the entire angle, angle LSC, is 90 degrees because perpendicular lines form right angles. We can also conclude that angle 1 is congruent to angle 3 by subtracting angle 2 from the two congruent angles LSB and ASC. We can also conclude that the measure of angle ASC is 70 degrees because it's congruent to LSB, which was given as 70 degrees. And then twice we can do 90 minus 70 to get the measures of both angles 1 and 3 are 20 degrees. And then we can fill in that angle 2 is 50 degrees because that's what's left to make the 90 degrees required in angle LSC. In this lesson, we looked at several theorems. The first four are all related to a group called the addition property. Theorem 8, if a segment is added to two congruent segments, the sums are congruent. Theorem 9, if an angle is added to two congruent angles, the sums are congruent. Theorem 10, if congruent segments are added to congruent segments, the sums are congruent. And Theorem 11, if congruent angles are added to congruent angles, the sums are congruent. And then Theorems 12 and 13 are each two-part theorems, and they're both part of a family called the subtraction property. Theorem 12, if a segment or angle is subtracted from congruent segments or angles, the differences are congruent. And Theorem 13, if congruent segments or angles are subtracted from congruent segments or angles, the differences are congruent.